Hi everybody. Since we didn't have time to go over the answers to the in-class activity, I thought I would make a short video where I walk you through my synthetic routes for making each of these different molecules. So let's go down onto the bottom of the page and I'll use some scratch paper. The first compound we have looks like we've got an alcohol on it and an ether on it. The first thing I do when I look at alcohols is I look to see if there's any functionalization in the alpha or beta position. So remember that your alpha position is the carbon that is directly attached to the alcohol. The beta position is the carbon right next door. So if I look at this, I would say the alpha carbon isn't really that functionalized, that carbon in the green, but the blue carbon is. So now what we can do is we can take a step back and we can say, all right, maybe we added some sort of nucleophile into this beta carbon and did a ring opening of an epoxide, because that's the one way we've learned this term to functionalize a beta carbon. So looking at this, I would say, well, maybe this could be our nucleophile, and maybe this side of our molecule was a former epoxide. Okay, so now let's break it down into the previous step. For looking at our nucleophile, we've got an alcohol with 4 carbons or fewer, and then we would need some sort of epoxide, and in this case we want 2 methyl groups coming off of one of these carbons, right? Now we have to ask ourselves, all right, how do we add these nucleophiles together? Do we want this ethanol to be deprotonated and be a strong nucleophile, or do we want to add this under acidic conditions? And in this case, if we look at the carbon we're attaching it to, we're attaching it to a tertiary carbon. And if you remember, strong nucleophiles don't typically add to the tertiary carbon. However, under acidic conditions, you can get weak nucleophiles to add to the tertiary carbon. So we must have some combination of this epoxide, ethanol, and I'm just going to write acid in brackets. Alright, so we're almost there. This alcohol already fits our criteria of having 4 carbons or fewer. However, we need to make our epoxide. So let's take a step back from our epoxide. We'll say, well, how can we make epoxides? Well, we can make them from alkenes. So we can say, all right, we need to have this alkene, react it with MCPBA, and that will give us our epoxide. Now, if we want to make this alkene, we could do this through any sort of elimination reaction from an alcohol. So we could turn that alcohol into a good leaving group and do an E2 elimination, or we could hit it with strong concentrated acid and heat and drive that elimination. So this was how I planned my retrosynthesis. You may have set it up a little bit differently. The main thing to remember is that anytime you see beta functionalization, you can think of an epoxide ring opening. And when you do an epoxide ring opening, pay attention to whether or not you're adding to the more substituted side or the less substituted side of that ring. You want to make sure that you get the correct regiochemical product. Alright, now let's look at problem number 2. Problem number 2 had the same guidelines, but this time if we look at it, we have an alpha functionalized carbon. We don't really have any functionalization coming off of the beta position. And so if we think about this, we only know really one way to functionalize the alpha carbon next to an alcohol, and that is through a Grignard reaction with a ketone or an aldehyde. So if we look at this, we could say, all right, maybe this was our nucleophile, and maybe this was our former ketone or aldehyde. In this case, you can see we have 2 carbons coming off of it, so it must have been some sort of former ketone. So let's break it up, and we could say our former ketone must have looked a lot like acetone. And in order to add a nucleophile to a ketone, or an aldehyde, or an ester for that matter, we need to add in some sort of Grignard if we want to add in a carbon. So in this case, we're going to add in methyl magnesium bromide. And then remember, after you combine everything together, you need to protonate this at the end. I'm going to leave this out since I'm just doing retrosynthesis, but you do have to quench your reaction at the end. So let's see how we can make this ketone from an alcohol. Pretty straightforward. We could take isopropanol plus some sort of oxidant, and in this case we could use PCC, we could use chromic acid. There's a lot of different oxidants we could use to go from isopropanol to acetone. Alright, if we look at methyl magnesium bromide, we can break this down and we can say, well, in order to make a Grignard reagent, we must have started out with an alkyl halide, which was methyl bromide. And we can make methyl bromide directly from an alcohol, specifically methanol. And we could use a reagent like PBr3 to change that alcohol into a bromine functional group. And remember, with making a Grignard, you only need your alkyl halide and elemental magnesium. Alright, so that's my synthetic plan for problem number 2. Now let's look at problem number 3. In problem number 3, we're going through a conversion from an aldehyde into a ketone. So we're trying to make this ketone over here, and we're starting with this aldehyde on the right. So the question is, how can we move this around? And this is where things start to get a little bit tricky. So what I'm going to do is I'm going to do a forward synthesis plan this time. So we're going to start out with our aldehyde. Now the question is, how can we interconvert between an aldehyde to a ketone? We can't go there directly. We don't have any mechanisms or routes available to do that. However, if we look at our aldehyde, if you remember, we can reduce this. So I'll do sodium borohydride, in some sort of alcohol solvent. And now when you do this, you get your primary alcohol. With our primary alcohol, we could eliminate this and form some sort of alkene. So let's look at this. If we get this alkene, now we're getting one step closer. So the question is, how are we going to eliminate this? Well, there's a couple different routes. You could do something like tosyl chloride and pyridine. Turn that alcohol into a good leaving group, and then once you have it as a good leaving group, you can eliminate it using a strong base. So I'll use sodium ethoxide, and we can get an E2 elimination to our alkene. Once we have this alkene, we need to get this oxygen installed to this carbon. So if we look at it, it looks like standard Markovnikov addition of an alcohol. In order to do that, we need H3O plus. Specifically, we need it dilute, so we need it to have a lot of water in there. That way we get Markovnikov addition to the more substituted side of the alkene. Now when we do that, we're one step away. We've got our alcohol. Question is, how can we switch from a secondary alcohol to a ketone? And this requires the use of an oxidant. Remember, you have your choice of oxidants. You could use PCC or Na2Cr2O7, that's sodium dichromate, H2SO4, and water. We have to use sodium chromate if we're trying to oxidize anything beyond a ketone or an aldehyde, but in this case, since we've got a ketone as our desired product and a secondary alcohol, PCC or sodium chromate will work. Alright, so let's take a look at problem number 4 on the in-class activity. If you look at it, again, we've got a situation where we've got a beta functionalized alcohol, and in this case we've got a cyano group or a nitrile coming off of that beta position, which means that the precursor to this final product must have been some sort of epoxide. So let's try to convert our alkyne starting material into some sort of alkene and then turn that alkene into an epoxide. So to speed things up, I'm going to abbreviate the phenyl groups as pH. And we've got two different alkenes we can look at, right? We could treat this with H2 and Lindlar's. And if we treat this with Lindlar's catalyst, that means that we'll get our cis alkene. Whereas if we treat this with elemental sodium and liquid ammonia, we'll get our trans alkene. So let's compare both of these. Here's our trans alkene. And then we'll treat these with MCPBA and MCPBA. Okay, in this one, we've got our epoxide, where both phenyl groups are going to be on the same side, because our starting alkene had both phenyl groups coming off of the same side of the alkene. So in this way, they're going to be cis on the alkene, they're going to be cis on the epoxide. Whereas with our other alkene, we're going to have a trans alkoxide. So let's just put one of these phenyl groups coming up and the other one going back. And we would also run into a set of enantiomers with our trans alkene. The top one, we don't have to worry about the enantiomer because it's a meso compound, but the bottom one we would have a set of enantiomers. Okay, so now let's try to ring open this using sodium cyanide. So I'll write NaCN, NaCN. Because this is a strong nucleophile, we don't have to have it attack the tertiary carbon, and we don't have a tertiary carbon, but we can ring open this. So let's compare both products. Have it ring open like this. Now when we do this, we've got oxygen, we've got our cyano group pointed down, this phenyl group is still going to remain a wedge, and this phenyl group is still going to remain a wedge. In this case, we would also get a mixture of enantiomers out because that cyano group could attack this carbon on the left instead of the one on the right. So you might get a mixture of products out of this. Or you will get a mixture of products, I should say. If we do the other one, we'll get a similar situation where we'll have phenyl group coming up. We'll have a phenyl group going down like that. And there we go. And now we can just protonate it and get to our final product. So I'll just write H plus in brackets, and we'll be able to get to our final product. The question is, which final product is the one that we want? If we have this one, we have slightly different stereochemistry than the one on the bottom. So let's finish drawing these out, and then we'll look at which one has the correct stereochemistry. And CN, and we've got our phenyl group. There we go. So let's assign R and S to our stereocenters here. I'm going to label this one as our red carbon. If we go through and we try to label this as R or S, we could go through it and we could say, all right, this one's going to be priority 1. If we go over here, this would be priority 2, and this would be priority 3, right? So if we look at this, we'd be going counterclockwise around the ring, which means that this would be S. And then if we go over here, we would start out with a carbon that's triple bonded to the nitrogen. Or actually, I take that back. We'd start out with this carbon, which is bonded to the oxygen. And then we go 2, and then 3. So again, counterclockwise. And this carbon would also be S. If we go down to the bottom, we can tell that this stereocenter is the same. So this one will be S. But the next one that we have, whoops, this should be a pH. Sorry about that. But this one, we flip the stereocenter. So this would be an R stereocenter on the right. All right, so it's important to remember that we would end up with a mixture of enantiomers for both of these. So for the top example, we would get a mixture of the SS enantiomer and then the RR enantiomer, where the one on the bottom we would get a mixture of SR and RS. All right, so now let's go look at our desired product. If we look at our desired product, we could say, all right, let's look at this carbon. This would be 1, 2, 3. Whoop. So this would be counterclockwise, which means that this would be S. And now let's do the other one. Start out with this. We'd go 1, 2, 3. Counterclockwise, that means this would also be S. So in this case, we want the SS or RR enantiomer, which means that we must have used this cis alkene intermediate. We must not have gone through the trans alkene intermediate, otherwise we would have ended up with the incorrect enantiomer. Alright, again, it looks like we've got an alcohol, and we could say, well, did we alpha functionalize it? Well, this carbon over here is already in our starting material. So instead, it looks like we added on some sort of functional group onto this beta carbon, one carbon away from that alcohol that was on our final product. So this makes me think of an epoxide route. So let's start with our starting material, and it looks like we need to change the starting material into an epoxide. So if we do this, we've got MCPBA. That will change this alkene into an epoxide. I'm not too worried about stereochemistry here because we really don't have any, so I'm not going to show dashes and wedges. Now the question is, how can we get this nucleophile, meaning this propyl group, to add on to the less substituted side of our epoxide? Well, we know how to make carbon-carbon bonds onto epoxides using a Grignard. Grignards are strong nucleophiles, which means strong nucleophiles will go after the more available carbon. So we must have used propyl magnesium bromide in step 1, and then in step 2 we probably quenched it with some water, and when we did this we were able to get to our final product. So pretty straightforward. I know I saw some people in class doing ozonolysis on this alkene, which gave you a ketone, and then you did a Grignard reagent into that. You could do that. This route might be a little bit easier. That way you don't have to actually do the ozonolysis step, which in practice is a little bit tricky. Okay, let's look at number 6. Number 6, again, it looks like this alpha carbon probably wasn't directly functionalized because we're missing a carbon here. We don't have this carbon to add in as a nucleophile directly from our starting reagent. So it looks to me like, again, we've got a beta functionalized carbon. So let's go through and figure out how to add on this guy as a nucleophile onto this beta functionalized position of our alcohol. Again, this means that this portion of our molecule over here must have been a former epoxide, and we must have added in this blue chunk as our nucleophile. So let's break it down. In order to turn our starting material into a nucleophile, all we need to do is add in magnesium and something like diethyl ether, some sort of ether solvent that will stabilize our Grignard. Now when we do this, we've got MgBr. We've turned this carbon into a really good nucleophile. And if we react this with simple ethylene oxide, this carbon will add into either side of the ethylene oxide, ring open it, and then in step 2 we can quench this with water and we can get to our desired ring opened epoxide or our beta functionalized alcohol. Alright, so we're almost there. Next one, if you look at our product, you can see clearly that we've got some sort of ketone we need to make, and specifically if you look at our starting material you can say, well, this portion right here matches this portion right here. It looks like we functionalized a carbon that is directly attached to an oxygen, so this looks like alpha functionalization, not beta functionalization. So we probably did some sort of Grignard reaction with a ketone, an aldehyde, or an ester. So let's go from our beginning portion again. And again, we need to make this bromocyclohexane into a Grignard, so I'm just going to write Mg, diethyl ether. We do this, we're almost there. Now the question is, what did we start with prior to this step, or how can we add this into a ketone or an aldehyde? So let's continue on, and let's just say, for the sake of argument, that I add this into the aldehyde. Are we going to be able to directly go to our final product? Probably not. When we add this Grignard into the aldehyde, what we'll get is an alkoxide. So let's protonate that in step 2, and we'll turn this alkoxide into an alcohol. Now we're close. The question is, how can we turn the secondary alcohol into a ketone? And that's pretty straightforward. We could use PCC or our chromic acid route. Alright, last one. This one I thought was the trickiest. I saw a few people with a variety of different answers, but I'll show you how I was approaching this. I try to match up the carbons in my starting material to a potential site on my product. So in this case, I've got 3 carbons on my starting material. I'll just circle these 3 carbons here, which again makes me think, alright, we've functionalized that propyl group onto this green carbon. We somehow attached it covalently to that green carbon. And then if we look over into this position, we've got a functional group coming off. Well, this chlorine up here could have been an alcohol in a previous step. So maybe again we're dealing with a beta functionalized alcohol in some sort of intermediate step, and then at our last step we convert that into a chlorine. So again, this makes me think of an epoxide. So let's change this into a nucleophile, and let's say this portion of our molecule used to be a former epoxide. So let's change our propyl bromide into a good nucleophile as our first step. We'll just add in magnesium diethyl ether, and now we've got propyl magnesium bromide. Now what we need to do is we need to react this with an epoxide that has 3 total carbons, because if we look up here, we've got 3 total carbons in our former epoxide position. So what I'll do is I'll make this epoxide, and then in step 2, I'll quench this with water. Alright, if we look at this epoxide, we've got a strong nucleophile, which means it's going to attack the more accessible side of that epoxide, and it's going to ring open it in this direction, right? So if we were to put in arrows, this carbon would come in, attack here, and ring open the more accessible side. Actually, let me draw this a little bit differently. So I've got an oxygen up here, I've got my propyl group down here, and I've got this methyl group over here. We're not really concerned with stereochemistry because I said our product is racemic. When you ring open it, you've got this alkoxide, meaning the oxygen doesn't have its proton, but in step 2 we're going to protonate it with water, so I'm just going to change this into an OH. Now to change this alcohol into a chlorine, we can use SOCl2 and pyridine. When we do this, we get to our final product with our chlorine on there, and it's always a good idea to count carbons. So we'll say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We've got the correct number of carbons, and our chlorine is coming off of carbon number 2. So it looks like we've completed the entire synthesis worksheet. I would really recommend going through the practice problems at the end of each chapter just to practice planning out your routes. You're more than welcome to use your map and study aids. However, just be sure that by the time the exam rolls around that you become really comfortable with 2 new types of reactions. The first one was ring opening epoxides, either under acidic or basic conditions, and then Grignards adding into ketones, aldehydes, and esters. Alright, good luck studying, and let me know if you have any questions.